Hello, class. Welcome back. This is lecture 6, camera perception part 2, 3D perception. Here is the outline. Lecture 6 has 4 parts. I'm going to start with 3D object detection, and then move on to online mapping, and then 3D occupancy prediction, and then temporal fusion. 3D object detection has 4 sub parts. I'm going to through one by one. 3D object detection is quite different from 2D object detection in a sense that we need to detect objects in 3D space. For robotics, especially for autonomous vehicles, we are dealing with 3D space plus time. So we need to be able to detect object in 3D space. Um, so let's go over these definitions, what 3D object detection is about. The objective is to detect the existence of objects and localize them in 3D coordinates. That includes binary classification, sensor position, 3D size, and rotation regression problem. Um, so let me move on. So this slide is comparing 2D object detection versus 3D object detection. 2D object detection, we only need to identify, it was a bounding box problem in perspective view, image view. And to identify that, we just needed to regress these values and find out the class, which is the classification problem. But as we move to 3D object detection, it gets a little more complicated because we need to be able to regress this value, which consists of a location, XYZ, and then the orientation. Um, so it has 7 values instead of 4 values in 2D object detection. The way it's evaluated is similar to 2D object detection. Um, so we compare the prediction output with ground truth using the same true, false, and then precision recall computation calculation. So recall is how many of objects are detected. Precision would be how many of the predicted results are correct. So this slide shows there are 2 ground truth here and here. And let's say your model output gave you one object here and one object here. Then this is going to be true positive, but this is going to be false positive. And then you missed one ground truth, which is false negative. So similar to 2D object detection. But note that when you determine whether it's correct or wrong, true or false, there are different methods. um, let's say here, um, the model is also going to output a score. Sometimes it's called confidence score, indicating confidence in detection. Um, and oftentimes, in old days, we had to use non-maximum suppression to determine to remove one's predicted results with low um, confidence, so that we don't have too many wrong outputs, such as false positive. So there is trade-off. Usually there is a trade-off. So usually you compute this curve, which is called average precision curve. So you change that threshold score, and um, so you find the value, the threshold value that maximizes the accuracy, which is maximizing this area under the curve. Okay. So with threshold changing, you are going to go through this curve, and you want to find a threshold that gives you maximum area under that value. Okay. So that is going to give you maximum performance. So that gives you what 3D object detection is. And let me move on to history and some of early methods. Camera-based perception has you can classify methods into two types. One would be 2D feature method, and the other one is going to be 3D feature method. 2D feature method takes the head takes 2D features and directly regresses a 3D attributes, whereas 3D feature method, you project the 2D feature onto 3D feature tensor for the 3D task header. Each method has pros and cons. Um, for instance, 2D feature method is usually computationally more efficient, gives you faster inference speed, but it's not it's less 3D or bird's eye view task friendly. And in the old days, it used to perform lower accuracy. But these days, people found a way to improve accuracy for direct 2D feature methods too. 3D feature method advantage is it's very intuitive, meaning that it's 3D task friendly, because you're reorganizing the 2D feature, image feature onto 3D space or bird's eye view space. And used to give better accuracy, but now it's comparable to 2D. So 2D feature method is now comparable to 3D feature methods. But usually it requires this view transform um, stage module, which adds more computation. So, but it's more intuitive. So if you look at this history, this is how different models have evolved over time, proposed over time, and you're looking at 2D feature methods in the upper side, and then you're looking at 3D feature methods in the bottom side. And I would say um, here, before 2021 or 2020, I would consider early works, and that would be there would be Mono 3D, CenterNet, pseudo lidar. And then after that, there is famous LSS, which evolved into BB depth. And then there's also popular BB former, and then another popular high-performing network called PTR, which evolved from DTR 3D. Let me introduce two early method. One for ED, a 2D feature approach. It's a CenterNet. So like I said, you use 2D feature directly to regress 3D attributes directly from the 2D um, features. So the main idea is to find the center point. So that's why it's called CenterNet. So you find the center point and then you find um, the box for that. And then after that, you compute 3D size, depth, orientation, and so forth. So it used to be more efficient because you're directly using the dense 2D feature, no view transform, um, and it's very uh, image friendly, which is so because it's 2D, it's directly using 2D features. Um, and here's loss functions uh, to identify those classes and regress position and orientations. And then another popular famous 3D feature, early 3D feature approach is pseudo lidar. It's called pseudo lidar because you use depth map. You compute depth map first, and then you project that into 3D space. Then it's going to look like LiDAR point cloud. That's why it's called pseudo LiDAR. So it has nothing to do with LiDAR. It's just it's camera perception method, but um, it uses dense depth map network, and you project that into 3D space. Um, and by doing that, you can use LiDAR detector, LiDAR detection head. So with at that time, there was also development of LiDAR perception networks. And by doing this, we can use LiDAR detection module, the head. So that's explained here. So you can use stereo or mono, and then you do depth estimation. In computer vision, there's whole lot of research in depth estimation, dense depth map estimation work. So you can use existing dense depth map network, and then you can you can get the dense depth map, and then you can um, change representation to 3D space. By doing that, we can use 3D object detection network that were already developed for uh, LiDAR detection model, which used to use voxel space. Here is more description, but let me move on to the next slides. The LiDAR detector is going to be discussed further in detail in lecture 7. So let me move fast here. Okay. All right. Let me introduce recent baselines. So with these baselines, I'm going to introduce 3 view transform approaches. Okay, there are 3 view transform approaches, um, or 3 families of 3D perception models. Um, the first one is forward projection, second, backward projection, and then third would be 3D query approach. Let me go over these one by one. The first one would be forward projection. The working principle is as follows. 2D pixels take the initiative in projection, and 3D space passively accept features from the images, which means we are projecting 2D image features onto 3D space, which could be either voxel, like this one or this one, or we can also project onto bird's eye view space. Um, Famous, one of the early um, models that use this forward projection approach was lift splat shoot. It's called LSS. So this was one of the early work that used this forward projection approach. What it proposed was you already have um, there's a little bit of delay. Okay. So we already have sort of like pseudo lidar. Depth is important um, to regress to compute where the objects are. So and to create this 3D feature, which means features on in 3D space. What they did was what the authors did was project 2D features from the perspective view onto 3D tensor space. When you do that, we have uh, depth information. So what they did was use that depth information and use that when projecting 2D feature onto the 3D space. So the operation they used was outer product. Um, So which means you're going to, oh, here. So you're going to have such dimension. And if you look at this in tensor, 3D tensor space, it's going to look something like this. So this matches, right? This matches with this space. So from deep learning perspective, it's, you know, uh, cubic space tensor with features in the tensor space. But it, from a physical perspective, we are looking at frustum. So it's called a frustum feature. So what that means is it's considering the field of view of the camera. So image, this is image feature. So on image, it's two-dimensional. But then when you actually project that onto the 3D space, it's going to have frustum um, tensor. Okay. So that's the main idea. Um, and lift simply means you take the 2D feature and then project that onto 3D frustum. And then splat simply here means you're going to collapse, aggregate features from 3D to 2D, which is bird's eye view. So it's so it's going to be so it's easier to compute. I mean, less computation um, compared to tensor computation. Um, and then LSS evolved into another model, which is called BV depth. So BV depth actually improved the accuracy of the depth part. So people knew that perception camera is not very predicting depth from 2D image is ill-posed problem, and its accuracy, depth accuracy is not very good. So people tried to improve the accuracy of the depth um, by using different methods. So for instance, here you use LiDAR point cloud to provide extra supervision for the dense depth map. And then you also have depth refinement here. And then you go through the regular detection head. So this is a BB depth, which improved performance over LSS. The next one is backward projection. So what this does is, I think that the name of these projection methods are somewhat misleading because people call it backward projection, but I think it's still forward projection in a sense that you're projecting image feature onto 3D space. But people call it backward projection because it uses attention and uh, which uses query, and the query is either voxel or bird's eye view tensor. So you use that query as an input, and then you get um, features from 2D feature space to 3D space backwards, because query was what is given as an input, and features are sort of providing features. So yeah, so that's why it's called a backward projection. Um, and the main difference is that uh, for BV depth forward projection, you already have you already have depth prediction. So you do have, this type of or this type of distribution. You have prediction, depth prediction. So your 2D feature is going to be emphasized around this point. However, for backward projection, um, it's not always the case, meaning that the features can actually project onto multiple um, uh, you know element in the tensor. And that's why it's prone to false positive features. So people try to improve that further. This is so that was a working principle of backward projection, and one of the uh, you know famous early model that uses backward projection was beamformer. So basically, they use attention to take care of the view transform from 2D feature to 3D feature by using attention and by using 3D query. So beamformer used bird's eye view query. So you don't have to do collapse from 3D frustum to BV. You can directly use BV query, and it'll learn where to get the feature from data and uh, you know, you know, backward gradients. So the main idea is adopting the backward projection principle. So you use learnable BB query, and it'll look up, proper spatial features from multiple cameras. Here's more details. Please spend more time on these details and try to understand how BB works. BB is one of the most popular method people use nowadays. Okay. Let me move on to 3D query approach. Um, this is 3D query approach is also attention method. But the main difference from the backward projection is that it doesn't actually have view transform, because it uses object or instance query, and then directly gets 2D features. So here's the query, here's the 2D feature, and then, but of course, you do need 3D position encoding, so that the attention can identify where these features came from. Okay, just like any other attention and transformer. So by using these object instance queries, we can avoid view transform. So there's no view transform. direct 3D detection from 2D features. So that's one of the big advantage and difference from backward projection approach. And one of the recent high-performing model is PTR. It uses this 3D query approach. So you can see that here's after 2D backbones, you have set of 2D features, and then here's the positional 3D position embedding. And then after position encoder, you directly decode. So it's a header, right? It's a decoder. Right. Let's move on to multi-camera fusion. It's also called spatial fusion. Okay, we just covered view transform, and that's going to be related to this topic. Um, it's very closely related. So here, this section, we're going to learn how we can aggregate or fuse uh, single image features with other camera features. So in the case of autonomous driving, we have multiple cameras, and when each camera, when each image goes through the 2D backbone, we have a set of 2D features. But if we have multiple cameras, we have multiple set of 2D features. Then the question is how to process them when it comes to 3D object detection. Well, rather than running each 2D or 3D feature separately, it'll be best to um, aggregate them, fuse them onto a single um, bird's eye view or 3D space, and then process them in one shot altogether. Then the question is going to be how to fuse them, how to fuse multiple camera 2D features. So that motivation is described in these two slides. And here are the three approaches we're going to learn in this lecture. The first one is non-lawnable fusion, simple operation, such as sum or average. BB depth is one that uses such a simple fusion method because this is very closely related to the view transform method. And we'll talk about that in the following slides. And the second approach is BB query fusion. It uses attention. And the third is going to be instance query fusion, which is attention approach. BB query fusion, one representative model would be BB former. And in the case of instance query fusion, PTR is the one that uses such a fusion approach. Let's go through one by one. Method one, the non-learnable fusion. The main idea, working principle, is you project a 2D feature onto, let's say, bird's eye view feature space. And if you do so, you're going to have overlapping areas. This is not exactly correct, but let's say you have cameras facing these direction, field of view, field of view, field of view. Then you have these overlapping areas, and the question is how to handle them, right? One simple operation we can do is sum or average, um, features that are overlapping in the overlapping areas. Um, so this is usually coupled with um, depth-based, uh, projection, forward projection method, which is BB depth or LSS. Like we just learned in the previous section, BB depth uses depth distribution and take outer product with uh, features, and that's going to create frustum features, 3D features, and then you can collapse them into bird's eye view feature. But like I said, it will create these overlapping regions. But you want to come up with a single bird's eye view or a single 3D um, tensor space with 3D features, right? So for these overlapping areas, we can simply use sum or average operations to handle that. Second method is BV query fusion. It's attention approach. It learns 3D feature in BV space to aggregate multi-camera 2D features. So let's say this is a query, or we could also use BV query, and then we are going to use attention and get, you know, uh, features with, weights, attention. So attention it naturally handles multi-camera um, fusion, or also called spatial fusion problem, because the attention itself can handle where to get the feature from. It learns where to get the features from. So when you have occlusions, it will automatically get features from both camera for the overlapping region, or it can have more weight on one camera over the other. So this is another figure that describes the method two for the model BV former. Okay, it has so this is the fusion part. So let's say we have 2D features, and then this part shows how we can create BV feature set from 2D features. So we learned, backward projection using attention in the previous section. And that's exactly what's happening here. It's applied here, but like I said, it can naturally uh, do the multi-camera fusion because um, here we have six cameras, six camera 2D features. And then if we use BV query Q and going through the learning process, the attention will learn where to get the features from. And it can handle multi multi-camera, multi 2D feature sets. So it's very uh, natural, um, and it can handle basically view transform and multi-camera fusion, spatial fusion together. Okay. And then there's also temporal fusion. Um, we will talk about that in the following section. Um, yeah, so this is BV Former video, um, but this is a PDF copy, so it's not showing, but uh, you can take a look. Method three is instance or object query fusion. Like we learned in the previous section, it directly detect 3D objects or instances from 2D features. And so basically there's no explicit view transform. But it does do, but it does view transform implicitly by using 3D position embedding, which is this part. I think this figure shows the concept better. This is model PTR. It has 2D features and then positional embedding encoder, and then it goes through query and decoder using attention or transformer. So this one is also it also uses attention, so it can naturally take the spatial fusion part or multiple camera fusion part because the we handle the space uh, view transform by having this positional encoding, and by assigning these positional encoder, it naturally knows where that 2D feature is coming from in the space, in the 3D space. And then this attention part can handle where to get the feature from for the detection. So again, attention can handle multi-camera, multi-image feature fusion naturally, which is a nice feature of using it. Okay. Let me move on to temporal fusion. So far we talked about view transform, and then we talked about multi-camera fusion, which is also known as spatial fusion. And then we're going to talk about temporal fusion. why do we need temporal fusion? Well, there are a few reasons. Um, for more accurate depth estimation and to predict or calculate velocity, we do need temporal fusion. In other words, we need to look at multiple images and tell speed of objects. Um, and another reason is to handle occlusions. So if something occludes, something gets occluded by another object's obstacles, then we cannot actually see it from a single image. But um, but if we use video, you know, instead of single frame, single image, we can actually tell there's an object behind that obstacle. And human can actually do that already. But for vision system, uh, we basically need video to be able to tell these things. In fact, like I said in the discussion session, um, video is readily available. Um, we are living in, 3D space with plus time. So it's very natural for any robotic system and autonomous vehicles deal with videos. That's the basically given inputs. So we should take advantage of that. And this is showing this figure is taken from Tesla AI Day, and you can see that um, wait, I think the legend is not showing. But basically, the orange is single frame based detection results. This this one is velocity, and this one is depth, distance. And you can see velocity. It's difficult to predict velocity. It's very noisy when you use single frame, but it significantly improves when you use videos. Okay. So just like Fourier transform spatial fusion, I'm going to give you three fusion methods. First one is simple concatenation, and second is attention, and third is recurrent neural network, RNN. So concatenation is simply concatenating two tensors and then process that, all together in the detection head, like shown here. And attention, we talked about attention many times in the previous sections. So and we know how attention works. So let's say we have current time step BB feature, and then we have previous time stamp step BB feature. Then attention can uh, give you fused bird's eye view um, BB feature that takes features from both current time step and um, last time step, T-1 time step, and then use that fused BV feature sets for detection head. The RNN works a bit differently. So RNN uses basically it's traditional RNN approach So you can use sequence of a set of BV features. So like in the case of two time step, you would have um, you need to have two set of BV features, and then you put that through the um, RNN module. Okay. Um, First method, concat. I think it's very straightforward. Um, you know, what we do by concatenation. So I'm not going to spend much time here, but BV depth is a model that used such approach. So BV depth basically uses simple sum or average operation for spatial fusion, and then concat for spatial temporal fusion. But if you but the downside is, so basically concat is the advantage is you're keeping all features, right? All current and previous features, and use that for detection head. But that means you are going to end up with large tensor uh, for detection head for input. So that's going to increase computation. And I'm listing more examples of using concatenation. Solo fusion is another one that used multiple um, time steps. So it used high resolution short-term fusion, and then low resolution long-term fusion, which actually helped uh, improving detection performance. There's another one, BVDET 4D. Um, please take a look, spend some time and take a look at how it works. Okay. Let's move on to second method, which is attention. So like I said, attention is naturally it's very it can naturally handle spatial fusion, and same applies to uh, temporal fusion. So when you have different set of BV features for different time steps, then you can put that into attention, and the output can be a fused feature set, uh, getting the right feature or informative features for detection um, from different time steps. So you can naturally handle that. But downside would be it fuses, right? So this fused BV feature set sort of aggregates, fuses features from different time steps. So it kind of loses, you know, time sequence, or it kind of loses, original single time step feature set. Um, Third approach was RNN. In academia, there's not that many models that uses RNN. Um, Instead, it evolved with BV former, which can easily handle both spatial and temporal uh, fusion. Um, but I will talk in the following slides, but Tesla uses RNN. So we should still pay attention to RNN approach. Okay. This is academic work, recurrent BV. It uses RNN to handle temporal fusion. So you take, so here is multiple um, multiple BV feature set, um, bird's eye view, and then it's going to go through RNN. So the way RNN works is you you the input to the RNN is can be current BV feature, and then it's going to provide fused hidden state, which is going to be used for the next time step. So the nice feature about this is you don't have to worry about, concatenating um, multiple time steps and feed everything into the network um, like previous two approaches. Um, but here, naturally, it can handle the memory of history. So, so RNN is actually uh, very, it's naturally fitted for sequence problems. So like when you have, sequence of images or information or whatever, then it can handle this sequence to sequence naturally. Um, Memory efficient in that sense, um, and it's scalable in the sequence length of the time step as well. So that's advantage, but then maybe it has some drawbacks that RNN has, which is in the long, if the sequence gets long, then the feature or the information can be diminished as for the long, long history information. So, like I said, Tesla uses RNN for their video module or temporal fusion. So if you take a look, it's a combination of video module and feature queue. So what feature queue does is basically it um, provides, let's say, BB feature set as a queue. So here you have um, so you have this is it. This is multi-camera features, uh, embedded onto bird's eye view feature space. Um, Note that this T is the time step. So you put this bird's eye view feature set with 60 time steps, and then you subsample that and come up with a video feature context, which has reduced size from 60 to 12 because 60 is too many. So it's subsampling uh, that size of the tensor. And then You put that into video module, and they used RNN. Specifically, they call it spatial RNN because RNN does not have space. Um, RNN is a sequence problem, like language, time type of sequence problems. Um, so it doesn't actually have that, space concept into it. Um, but they actually introduced this spatial RNN to make sure this RNN is working in space. In other words, the features we are feeding into this video RNN module, video module, has uh, uh, in 3D space, basically. Um, so I, I'm going to assign a homework on Tesla AI Day video. So please make sure you watch the video. It should be quite interesting. Okay. Okay, next section is going to be online mapping. We have two sections left, which is online mapping and 3D occupancy. It's so far we covered up to here, and then we have two more sections to go. So far, we mostly talked about 3D object detection with different baselines, view transform, multi-camera fusion and temporal fusion. And then here we'll talk more about, different tasks like mapping and 3D occupancy. Online versus offline mapping. Um, why online mapping? Um, As you know, we have second module of this course is dedicated for SLAM, which stands for Simultaneous Localization and Mapping, which is mostly mapping problem. So why online mapping? Well, we are going to learn SLAM, but we also need to learn online mapping techniques because we have offline mapping technology, but which is a big portion of robotics problem and very important, useful technology. But for autonomous vehicle applications, it can be quite costly and have limited scalability. Especially when it comes to updating maps in semi-real time. Um, we need to collect data and then construct maps from the raw data, and this takes time and efforts. And we are dealing with these problems nationwide. And if you want to scale up to globally, then you need to scale this into global mapping problem. So, which is not very practical. So, we talked about, you know, Waymo versus Tesla approach and talked about online, offline mapping. Waymo, their business model is to provide mobility service So they don't have to, um, they don't have to travel from any point A to any point B. Or they can collect data in a limited region, and then they can build a complete map, and then they can navigate in that space. So that's why it's often called geofenced autonomous driving. And that's what ODD is for level four uh, services. Instead, on the other hand, for Tesla and many other automobile manufacturers, they have to sell vehicles globally. So, and their driver assistance systems or autonomous driving functions must be able to work in many different countries. So scalability is a major problem, and it's very important for their application, their market. So that's why Tesla also sells vehicle. They need to sell vehicle and equipped with autonomous driving capability. So they decided to drop the offline HD map construction and decide to go with a real-time online mapping approach. And this can help, scalability, and, it doesn't require real-time map updates. Let's say there's a construction, um, you know, online mapping can handle that kind of uncertainties. So in this section, we're going to learn what online mapping task is about, and we'll talk more about the offline mapping in the second part of the course. The objective is to construct a surrounding map from sensor inputs in real time. Um, so estimate local semantic maps with onboard sensors and computation. Uh, and then map, it can be described by a set of map elements with different categories, such as lane divider, road boundary, crosswalks, road marks, traffic sign, you know, all of that needs to be detected. Um, when it comes to representation, mapping representation, there are two representation, rasterized versus vectorized. Rasterized map is, you can think of it as image pixels. So you have, let's say you have bird's eye view space, and you are going to, classify each pixel or each space um, with different classes. So, for example, here there's a traffic agent marked with yellow. You can mark different lanes using different colors. Of course, it needs to be, it's a signal, right? This is just a visualization of those signals. On the other hand, if you move to vectorized map, um, it uses vector, node and edges. The main difference between the two, rasterized versus vectorized, is vector is more efficient, more memory light, because the rasterized map has many pixels, and you have to have uh, information for every pixels, right? Every space. So it's very cool in terms of visualization, but it's not very computer friendly and memory heavy. On the other hand, vector is very computer friendly because it's a concise, compact, lightweight representation, and computer can use these node and edges um, for different purposes, planning and as well as uh, storing these information as a map. So these days, vector is um, much more widely used when it comes to representation. Um, and rasterized map is more used for visualization. But sometimes rasterized map can be useful. Just depends on what problem you're dealing with. Here is losses and metrics. Please take a closer look um, how these vectors are calculated to evaluate accuracy and to train models using losses. I'm going to introduce a couple of models. The first one is MapTR. MapTR uses backbone, 2D backbone, and then view transform, 2D to bird's eye view, and then we have bird's eye view features, and then we have different decoder for mapping. So this is the different. So up to here, same backbone as 3D object detection. So the feature, the information is same. But for mapping task, we need different decoder. And MapTR uses transformer for the decoding part. Um, and it uses, you know, tokens and transformer and nodes and edges to provide output in the form of a vector. Okay. And then the second model I'm going to introduce is Instagram. This is um, work from my lab a few years ago. And you can look up online if you like for more details. But basically, the main idea was use GNN for the decoder. Um, Instagram also used same backbone, so 2D backbone, and then view transform with a BV feature. And then here the main difference is from here on, and we use node and edges um, to to make it more vector friendly uh, feature. And then we have association part. So we need to identify which node and edges are connected. So here we use attentional GNN to identify, to find out the association between these node and edge elements to come up with vectorized HT map. Okay. I'm not going to go through details. For details, please read paper. And if you have questions, we can talk more about this in discussion session. Okay. This is showing it, the performance was great back then, years ago, but now there are other approaches that improved performance further. Okay, next topic is 3D occupancy. So why 3D occupancy? So if you use 3D bounding box, there are all kinds of objects in real world, but we cannot actually define classes for all those objects and label them and learn them. So it's not very scalable. It's not very practical. There are just too many objects out there. So what they did was, and the shape of these objects can vary a lot. But object detection usually have 3D bounding boxes. So in the case of this construction vehicle, this 3D bounding box is not good enough because it's not including this part. But then if we make the bounding box bigger, something like this, then it's going to be too conservative, too large. The bounding box would be too big, taking up too much space. So, and oftentimes we need to be able to handle these, non-canonical or non-regular shapes, but still be able to navigate, drive next to these, objects with different shapes. So people came up with 3D occupancy task to handle these things. And what it is it's basically a 3D segmentation problem. So we voxelize 3D space, and then uh, we classify, we identify whether it's occupied or not, free, occupied, uh, unobserved, or unknown. We need to be able to tell that. So is it free space? Is it, occupied? Is there something in this space? And then further, we want to be able to tell what it is. So is it static objects? Is it dynamic objects? Is it car, bus, building, tree, right? Is it something very soft or very rigid? We want to be able to tell these things, right? So if we have complete and very accurate 3D occupancy, then we can do uh, many things out of it. And this is loss and metric, just like any other, very similar to other metrics for semantic segmentation. But at the same time, segmentation and this type of task and metric has a problem of, average problem, meaning that there are many pixels for segmentation, and for 3D occupancy, there's, many, uh, voxels in one scene, right? So if we evaluate these things for per voxel, per space, per element, then if we compute these IOU, then it's going to be very, one scalar value that represents the whole thing. And that may be too simplified value that to represent the quality of of or accuracy of the occupancy performance. So this is a very average sense metric, so it's not perfect. There are three approaches when it comes to 3D occupancy models. First would be bird's eye view. Second is tri-perspective view. Third is voxel. We already learned about these representations, right? So 2D representation, 3D voxel representation, and then one new representation I'm going to introduce here is tri-perspective view, because voxel is too compute heavy, right? So too many elements. But then 3D occupancy needs to be able to hold information in 3D space, meaning that bird's eye view may be too compact. It's two-dimensional tensor, right? So voxel is too big, BV is too small. So people came up with this idea of TPV, which holds three perspective view. So one view would be, let's say, if we have three-dimensional space, we have three axes. So this would be one dimension, and this would be one dimension, and this would be another dimension. So this is simplified representation of a voxel, right? So, or this is three times more compute than BB, okay? Rather than increasing another dimension. Okay, so this will be it for today, lecture 6. So today we covered 3D perception, and then we're going to move on to LiDAR 3D perception, and then we're going to have another lecture on recent, perception work and some of the state-of-the-art works in the last lecture, lecture number 8. Okay, thank you for your attention, and please let us know if you have any questions. Okay.